Okay, so welcome back to CAP 6640, and today we will be continuing what we started last time by going a little bit deeper, not so much, but a little bit deeper into word embeddings. We will have an example on the gradient descent, and then a recap of word to Vic, and then talk a little bit about some techniques. So we'll go over a skipogram with negative sampling, with a window-based representation, and an example, then count-based versus direct prediction for language models, and then talk about word sense and how to evaluate word vectors. The order does not matter here, but this is more or less what we will cover. So again, the objectives is to highlight some logistics, always going to be the first item that we have. Highlight some logistics, go over the gradient descent example, then skipograms with negative sampling, window-based models, and evaluation techniques and word sense. And before I get started, I want to stop for a minute and ask if you have any questions from last time. Yeah.
At the end of every month,
so I have a logistics slide. Why don't you go over the logistics, and then if the question is about logistics, you ask the question in the logistics. Or oh, this is not logistics. Okay, go ahead. Not logistics. No, carry on.
What that lab is.
So the question here. So for those who are going to be watching this, I want to repeat the question so that you have the full thing out there. So the question here is that what is the point of the labs that we have at the end of each module? And the answer to this is that it's something that is for you, totally for you to try, exercise. I give you a prescriptive kind of description. How to go about this lab, what to do, what to install, what to try, what to code in, and then what to look for and what to expect, and then what kind of observations they can make on. And the reason for this is that because we are a computer science department. I understand that some people here are not computer science, not have computer science background, and so I cannot basically make this part of the course as part of the evaluation. But at the same time, I want those who are here for some more coding experience to be able to have that experience. It's not going to be part of the grade. You're not supposed to come back and give me some report about that. But to have the wholesome experience of this class, if you wish, as a computer scientist, I would encourage you very much to do those labs. Okay? So they're self-guided. So they are there, do them. You are supposed to do them. You are expected to do them, but I'm not going to, basically evaluate you on that. All right, so logistics, module 2 is released, if you have not noticed that. One reason I'm actually not releasing all the modules at the same time is because I update my slides, and then I want to just have the slides out there before I just release everything. Proposal will be graded shortly, and I'll give you back the feedback before this weekend, hopefully. The academic activity is due on 23rd. It's going to be tomorrow. Just do it if you're not that. Assignment number 1 is due on 26th. And then finally, the office hour is from 2 to 3 p.m. on Tuesdays. So far, the office hour has been utilized, but it can be utilized even more. And I'm going to be away February 6th to February 12th. We will have the lectures pre-recorded, but I'll kind of keep that here so that you do not show up to the classroom on those days. Yes, please. You have questions?
Just a quick input.
Yeah.
That the main thing I was going to do is look at other research, mine it for data. Then I was going to try and get my own, but I felt like the research that I was going to pull is going to be a little bit more polished, whatever I can do.
More what?
More polished or more kind of empirical.
Yeah.
Anyway, I guess I didn't ask this question before I put that in, but how critical is that we get our own data as opposed from pulling some data from research?
Not as critical. So the question here is that one of your colleagues here is asking that they will use some secondary source type of data sets, others data sets, and then they will have their own research and do their own data. And the question is how critical, how important it is for the evaluation in this class. I guess the evaluation you're asking about, the evaluation of this class, to use your own data. The answer is it's not really that critical. So I expect you actually to use others' data. If you have it, that is going to show a little bit more, be an indication of effort, and that will be appreciated, and that will be reflected in the grade, above and beyond, not for the basic expectations.
Or that I can replicate whatever I saw, more so like using the.
That is totally fine. Yeah, that is totally fine. Yep. Make it quick. Make it quick.
What are your expectations? Like one paragraph, two paragraphs, equations, examples?
Miss up the first assignment so I can give you the keys and then you just learn from it. Now I'm messing with you guys. No. So be sufficient. I think I have instructions there for that. So be sufficient. So you will see that a couple of lines will not be sufficient. So you have to explain your understanding using your own words, but not being excessive. I know that some of the students here just like write me books and I ended up like at the beginning penalize them and did not feel good about it, but like be sufficient. Use your own judgment. Yes, please. No, pre-recorded. So they're going to be pre-recorded. I'm going to just sit in my office and record the lectures and you do not show up. Yeah. Okay. And that's why like I'm putting it here in advance so that you just say like, hooray, I don't have to show up for this whole week. Yeah. Yeah.
But they don't appear in the web.
Right. Yes. So the question here is about the difference between the slides that I have already posted online and the slides that I bring here in the classroom. The slides in the classroom are updated. I keep updating my slides. The more I know about my topic, I get a little bit disappointed of like how they are presented and whatnot. If that is something that you want besides the recording, because the slides will show in the recording that you have, I posted the recording already. If you want the slides, the physical slides that I have here, I'll put them out there. So don't worry about it. Okay. Any other questions? All right. Good. Let's start. So we'll go over the gradient descent, and that is it's more of the ABC of machine learning. So I feel like everyone should not only like think of gradient descent as a black box, but they feel like what we are doing here. Eventually, the model itself is going to be a bunch of weights, but then how do you come up with those weights? And so this is what it's going to be about. So gradient descent, here's the equation that we had earlier. Basically, you have a bunch of parameters, let's call them theta. And you want to change those parameters, this like bunch of weights. You want to change them based on some objective. That the objective is going to be the predictive power of this model, how good it is going to be eventually at giving you some labels that are similar to the ground truth. Labels that you know for a fact that those are reflective of the true label, okay, true nature of an object. And so this is from the previous class. This is the equations on the side. So we have here theta and u. That's like what you'll eventually update. It's going to be theta old, the old parameters, minus something, okay? Minus alpha multiplied by delta theta, j theta, okay? And so alpha, we said, is the what we call step size or learning rate. And delta theta is going to be differential. J theta is going to be some function over theta itself, which is the parameters. And the updated equations for a single parameter is going to be, because I'm mentioning single parameter because this is what you're going to highlight here for a single parameter, is going to be theta in u for j is going to be the jth parameter in theta, in a vector called theta, is going to be the old one minus alpha, the partial derivative of j theta with respect to j, right? The partial derivative. Now, for you who do not know what is this, we'll go over an example that highlights the idea. So let's say that we have fx, and this is like general. It does not talk about machine learning, general. Like, given that you have an fx and you want to find out the solution for fx that minimizes a loss, okay? So that gives you the highest predictive power or the highest value for this function fx. And you can treat fx as instead of j theta. So let's say that you have fx to be x squared. So the first thing that we will do is that we calculate the derivative of x is going to be 2x. And the zero, like the derivative substitution at the value 0 is going to be 0. This is going to be the minimal value. And so you want to find out that minimal value, right? Using the gradient descent. Okay, that's what we want to do. That's what we want to achieve eventually. And so I said that you start with an initial guess. You make some configuration of parameters in your case. In the previous case, with you have like vector representation. You say like I want to start with all zeros. Not a good idea, but all zeros, or maybe uniform values, like whatever the size of the vector, I'm going to have 1 over the size of the vector, all the values, and then it changes those values according to some procedure called gradient descent to be able to achieve the optimal parameter configuration, or values and the parameters that give me my objective. So let's say that we have an initial guess and say like x equal 4. Then what we do is that we calculate f prime of x, and it's going to be equal to 8. And then you update x to be the new x, right? And we will make an assumption here about alpha here being some parameter 0.1. So a new x is going to be x old, that is the initial parameter 4, minus the learning rate. We assume that it's 0.1, alpha 0.1, multiplied by the evaluation of our derivative at the initial value. That was 8. 2 by 4 equal 8. So basically, we subtract the diff and the derivative, right, multiplied by the rate, that's 0.1. The diff and the derivative is going to be like 8 multiplied by 0.1. We subtract that from the initial value that we assumed, and it's going to be our new value. Make sense? This is like the basically empirical implementation of those equations. And then you have then f 3.2 equal to like f of 3.2 evaluated in the original equation, which was like well, f prime actually equal 2 multiplied by the value, the x, equal 6.4, and you repeat gradually, slowly until you reach the minimal value that you want to achieve. Okay. Now in this case, the minimal value is 0. We know it already beforehand, right? We are just like putting the cart ahead of the horse, right? But in reality, we do not know what is this value, and we want to reduce it as much as possible. And you expect that the evaluation here will get you down and then sometimes up, right? So you want to know which value is the minimal that you will be able to achieve. It's not really known. It's not like a 0. And this is what this does, okay? So the gradient descent, here's the neat kind of representation of it. You define the variables. You have predictions. There's going to be vectors of predicted values. Let's say that like the label itself, the ground truth was like y, and y could be y1, y2, y3. Let's say that we are talking about sentiment analysis. Could be positive, negative, or so-so. Positive is going to be y1, there's going to be 1, and everything else is 0. If it is negative, it's going to be 0, 1, 0, and then if it's so-so, it's going to be 0, 0, 1. Okay, so like for the y3, it's going to be the value triggered. The prediction is like whatever that model is predicting for you. You give it a sentence, and then that sentence is assigned a value that is, say, negative. It says negative. In reality, it could be positive. It could be like 1, 0, 0, and the case could be like in the output could be like 1, 0, 0, 1, and so that's what you have. What is that difference that we calculate? The loss, the gap between what is true and what's not true. You can use anything, but here we use like what we call the MSE loss, the mean square error loss, and we choose n to be 3. That's because there is a number of labels that we have in the output. There's going to be y1 through y3, and you calculate that Lj or whatever L as the difference between y hat and y, between the label that is predicted and the label that is ground truth. And there's an equation for calculating that. If you change that MSE to something else, loss function design is an open direction in machine learning. So, or not open direction, is not open anymore, but important direction in machine learning. And so you choose it, and then you can compute the derivative with respect to the prediction of value, like in this case, it's going to be with respect to y. You calculate that, and then substitute the values. So for this example, let's say that we have the initial values, say y was like 1.5, 3.5, and 4.5. That is the ground truth. And the prediction was like, say, y hat equal 2.0, 3.0, 4.0. That is exactly equivalent to what we have already had earlier. We have like, say, a value, initial value of 4, and then we want to just like find out what is the correct configuration for the value that gives you the 0, the eventual 0. So you do that, you calculate the gap between them. It's going to be like minus pairwise for like the y and the y hat, and then you get the derivative, and then the derivative is going to give you whatever weight, and you plug that in the equation above in the partial derivative to get the output. The partial derivative is then going to give you like where to go, left or right. Make sense? What is the step size of that? Whatever step size. What is the step size of that? Like how you go left or right? What is the step size? How do you decide the step size? Huh? You make it, right? Yeah, which is like 0.1 we said last time. So you pick it, and then like, you try a few of them until you what is right. And by the way, there are some optimizers that do the picking for you, right? Like AdamW or whatnot. If you do your project and just dig deeper into some optimizers for parameter configurations, you will find some of those optimizers, and they'll pick a few values and then like find on a small like epoch and then find which one would work best, and then like will pick it for you. Okay, you can have initial one and then, or you can have a dynamic, whatnot. Okay, so this is it. It's great. Why do we care about this? We care about this because we wanted to learn representation for words. So again, what is word2vec? The one that we had. Well, you iterate over each word for the whole corpus, predict the surrounding words using the word vector representation that we had here earlier, and using this calculation of outer given the center, and that's going to be expressed using this equation, and you update vectors so you can predict well your initial vector representation. Make sense? You update those vectors. Okay, good. Now we said that as you are going through the like the words, there are so many updates that you have to make, and this is a problem. This is what gives us kind of leeway into SGD, stochastic gradient descent. So the problem happens when just j theta is going to be this function indicator of the parameters that we have, all those parameters that we have for representation, is going to be basically a function of all windows in the corpus, potentially billions of windows. As you're like sliding through the windows, you're updating those weights for theta. Make sense? And this is very bad because updating like this every time you slide through the window billions of times for all those parameters is going to be a lot of work. Memory access, additions, subtractions, whatnot. Okay, makes sense? So this is a bad thing. So there is a solution to the problem. Well, there are a couple of things you can do. One, you can wait a little bit. Wait for too long is going to be bad because you are going to be missing meanings, right? You're not updating as frequently as you should and missing meanings. Or wait too little, but we are like in the too little. We are like in the perfect world of too little. You are updating like all the time. And that is the overhead problem. So the solution to this problem is SGD. So what you do is that you repeatedly sample windows, right? And update on those windows after that window particularly. And that window is not going to be like waiting for let's say for example 10 windows. No. Randomly you pick like the windows. Like this time I'm gonna update after a size of like 5. Like after 5 skips I'll update. The other one after 10, after 3, after 1. The window size itself is dynamic. That's why we have the stochastic random update. Okay, how random it is, there should be some clever way to deal with how often it is, right? And that's going to be based on some evaluation criteria, on the quality of the vectors that you have, and that is out of the scope. But this is the idea of SGD. So the same thing that we have done with GD, but then now you're not doing the updates like very slowly. You are doing them with jumps. Yes, please.
The updates have that helps you like how it learns, basically learn.
What do you mean by persistence? So the question here is that would the updates have a persistence over time? So what is persistence? Can you clarify? Yep. Yep.
And he's learning.
Yes. Excellent question. Very excellent question. So if you're talking about like this personalization, like imagine that the language coming from a single source, like an individual, right, is going to have some patterns of sort, distributionally has some patterns. Then would it make sense to have consistent type of sampling over that person's language to perform best with that person? The answer is yes, naturally yes. Because eventually what we are here doing is not really for a single person. We're doing it for like a large corpus of data coming from multiple sources. And so for that, it's very difficult to kind of say yes. But for that application, right. Okay, so any questions other than that? Yeah. What do you want? No, I don't have an issue. Yeah. Why do you think I have an issue? Oh, maybe from the previous guy. Yeah. Or maybe like those things here, the screens, was it? But I don't use them. So my students, no. Yeah. All right, thanks. Well, I mean, there is a problem, but I had to lie because we have to finish. And the problem is that the HDMI direct takes its configuration from the HDMI machine, not from my machine. And that's why I have to unplug this dock view every time and plug it here. But it's not our problem. This is going to go on YouTube and it's going to be embarrassing to say that. But, yeah. All right. So what is the idea here? The idea is that we want to skip. Basically, this is what we are saying. We want to skip those updates that we are making. We're not going to make update in every epoch, and we want to skip. And so basically, we want to skip because we do not want to update this quantity of probability, like the P all given C, for all possible words out there. And so you just like sample a few windows, and then you calculate the words within those windows, and then you have a distribution. This hopefully is going to be a rough approximation for the distribution if it had been done over all the possible windows. Okay, and so we implement what we call skipgram. I'm gonna like say a few terms, not define them properly, but then I'll give you the example, and then you will see like the proper kind of definition of them in place. So the idea is that we want to basically, eventually, train a logistic regression for a true pair that's going to be centered with actual. This is something that we did earlier, versus several noise pairs centered with random words, and then try to detect those true pairs in the process. Okay. Skipograms with negative samples, the overall objective function is going to be the same thing that we had earlier, but here we are simplifying things by having gt theta. And so g theta is going to be the average over all possible t, say windows, of gt theta. And the way that we calculate gt theta is going to be log theta of log the sigmoid function of the multiplication that we had earlier, plus some quantity. So the meaning of this one, what you do is that you maximize two words co-occurrence in the first log, and then make the two words that are different from one another as far apart as possible. Okay. So what is the procedure? How we do this? We take k negative samples using some word probabilities, like those words do not happen with one another, do not define each other by being neighbors of each other, because we define the word meaning by its neighbors. So you get those sample words, like for example, honesty and foxes do not happen. Well, they happen actually. It's the negative, but something of your choice, right? And we try to maximize the probability that the outside word appears and minimize the probability that random words appear around the center word. Make sense? Questions? Good. Okay. Why not capture co-occurrence directly? Why do not you do the co-occurrence directly, not only by sampling? Because if you want to capture the co-occurrence directly, you have to do that over a huge amount of possibilities. So window, similar to word2vec, you use windows around each word, not indefinitely. You capture both syntactic and semantic information from that. And then word document co-occurrence matrices will give you general topics, will not give you like the exact meaning, because they are going to be more diluted around a large context. All right, so here's the procedure, right? We are computer scientists. How many of you are not computer scientists? By the show of hand. We are not all computer scientists. So let's go over this a little bit slowly. IT is science, computer something, computer thingy, right? The IT. I mean, it's just computer IT. Okay, so what is the objective here? Is that we want to have this very fancy schmancy type of representation that we want to use for encoding meanings. So we want to have dense embeddings of a given word by predicting the context word, giving a target word. That is exactly what word2vec is, but we want to do it with a skipgram, with negative samples. How it works, the input is going to be your target word and its context window, and the positive sample is going to be word pairs from some corpus, say for example W target and W context, and the negative sample is going to be random pairs. Okay, so random pairs are going to be W target and W noise, and those are generated from some noise distribution. You do not have to have them actually as real word. You can have them as distributions already just driven. The training, you train a binary classifier to distinguish the real, the positive sample, from the random, that is going to be a negative sample pair. And the output is going to be embedding that capture the semantic similarities between those two words. Make sense? Good? Are we good? Okay. Advantage of this is going to be very efficient for a large number of vocabulary, because you don't have to do that based on the occurrence of all of the word in all the possible context. You already have that relationship coupled, right? And you can capture semantic relationship, like for example, analogies, similarities, whatnot, because you have that in the training, the positive. And this is widely used in all complex downstream tasks, NLP tasks like translations, sentence analysis, etc. Application of this one would include pre-training or pre-training embeddings, semantic search, etc., etc., etc. So there are many applications for that. I want to stop here a little bit and ask a question. We will use this term downstream tasks. What do you mean by downstream tasks? Huh? Like that's like what it means, but like what technically what does it mean? Like what if we are saying downstream task, that means there's upstream task, and it feels like I'm talking right now about an upstream task. So what is the upstream task I'm talking about right now? Huh? It's the embeddings, the embeddings. So when we say downstream task, we want to make a distinction between what we're trying to do right now, which is the embedding of the words, the foundation, and then the downstream task is going to be, and the foundation themselves are great, useful, but they're not really useful for whatever we're trying to achieve here, which is the actual machine learning, the actual natural language processing task, which is translation, sentence analysis, name entry recognition, and so forth. And those downstream tasks, what we mean by downstream tasks, is that something that we're going to build on top of those embeddings, on top of those vectors. We want to do an ER. Okay, that's what we mean by downstream task. Okay. So, any questions? Yeah. Downstream task. What? Upstream task. Well, the upstream task is like, so imagine that you have a pipeline, and the pipeline is a stream. You start of a corpus, a language utterances like CNN corpus, and the upstream task for a downstream task, things are relative. For the actual task, which is what you'll eventually do, is going to be the upstream, is going to be the machine learning wise, is going to be embedding, representing the contents into some way, or some task that is a precondition that has to be done in order to be able to achieve well in your downstream task. It doesn't have to be only the embeddings. There could be multiple early tasks that you have to use to do to be able to do well in your main task. Make sense? Okay. Come again? Yes, yes. It's a prerequisite for the actual useful task that we'll do.
The pre-trained embeddings are pulled from settings or some register. Where are they pulled from?
You can create them yourself. You can start with something and then just like manipulate it, fine tune it.
That'd be language, English.
The embedding itself. Oh, so the embedding itself for like say a bunch of words is going to be just a bunch of vectors, a bunch of weights. Those are the embeddings, and the way that you get them is like what we're describing right now. Yeah, yeah. And what we will mention like in a second. Also, you can do it in different ways. Yeah. All right. So window-based representation. Okay, we talk about like the like more abstract things so that we can scare people, so that they just like up there tight and then listening, and so that they can understand like what we'll do eventually. And what we'll do eventually can be even simpler than what we have mentioned earlier. How simple? There is this thing called window-based representation. Okay, so window-based representation. So what do you mean by window-based representation? You have a corpus of language, and then you start with a window. The window size is going to be whatever that you define, and then based on that, you calculate some odds, chances of words appearing in the language, in the document. Okay, and so let's say that we'll explain that with an example, so that examples are easier to understand. No theory, no mathematics, no nothing. And then we'll go to the mathematics where needed. So let's start with a window size length of 1, meaning that I care about the frequency of individual words. Okay, makes sense? Common window size used is going to be 5 to 10 in general. And this is symmetric, so it's irrelevant whether left or right context happens. And let's say that we have this language, this like bunch of utterances, this corpus that we have. I like deep learning, I like NLP, and I enjoy flying. Okay, and we want to represent this language in abstract fashion. So we get those, and then we will try to find for each individual word, we spell out all individual words on the X and the Y, and see like how each word define one another. We said that where M not equal J. Remember that in the equation that I mentioned earlier last week? And I said like, oh, that's because we don't want to calculate similarity between word and itself. So we just like zero everything in the middle. That is, I does not define I, like does not define like, and so forth. But how often I and like occur in my language in that order? I like or like I. Well, in my language, I like deep learning. It happened once here. I like NLP. It happened twice. So that's why I like is 2. Make sense? So I defined like and like defined I in this company type of notion of occurrence. Okay? Yes.
More holistic. I like deep learning and I like NLP. How would you categorize?
What do you mean categorize? I'm not really here talking about categorization. All I'm doing here is that I'm building a representation for the occurrence of words. And I'm saying like, you use a window of 1. 1 means like, remember when we said like window of 2 means that you can calculate 2 from the left, 2 from the right. 1 means like, the word before or after. Yeah.
It was like, I like deep learning and I like NLP.
Oh, I see. So it counts twice.
Okay.
So I like and I like, this is twice. Yeah.
So does it matter if they're in separate
So does that matter if they are in separate sentences, you mean?
So you have one sentence where the word shows up twice, and then the other sentence shows up once. When I mark it as 3, as it appearing.
Oh, forget about like, the structure of sentences. We don't care. We can have that all as a single string. And you can scan through the string with window. Scan through the string, all of it in window. Does that make sense? I mean, here, the reason why I'm putting it here this way is so that it mimics the actual language usage. So I say like the sentence, the sentence, the sentence. But for us, we start by feeding the model everything as a single stream of bits or bytes or characters. Right. Yeah. And we do that all the way. So now we have a representation of our language. Say our language here is just like this bunch of quirks, right? And so I have a representation of my language. I have a vector representation of my language. I is going to be defined as 0, 2, 1, 0, 0, 0, 0. Make sense? Good? Right? So like and enjoy define I more so than I itself, deep learning, NLP. The same rationale, the same idea that we had earlier. Make sense? This is good. This is a good start. This is a window-based counting. We counted. Yes, please. Come again? Which one? Which word? Lying. My mistake. Yeah. I had to abolish this slide just before I come here. My mistake. I mean, you can, like, flying can be there. I like, enjoy, deep learning, NLP. Yeah. Should be there. Flying. Okay. But the idea is clear, right? Any questions? This is good, right? Why do we care about like this very mathematically involved type of word to pick? Why do we care? Because imagine that you have 1 million words out there in the dictionary, and so you have the same problem that we had with one-hot encoding, right? It's slightly better because it's based on actual coherence, but it still have the same problem. So how do we solve this problem? We try to put this vector representation in low dimensions. Make sense? And one of those things is called the SVD decomposition. So here's how it works. So the low dimensional vector representation, the key idea is that you compress coherence statistics into a fixed size, short, dense representation that preserves the most informational structure. If you have taken linear algebra, this will sound silly to repeat, but the idea itself is very profound. So in linear algebra, what you can do is that any matrix, square matrix in this case, let's say it's a W, you can decompose it into 3 matrices: a core matrix and a upper triangle, lower triangle matrix. The core matrix itself, you can fix the dimensionality of that matrix and can be significantly smaller than that of the original matrix. And that's the idea. So, questions? All right. Smaller means you do not have to spend a lot of time to represent it. And when I say like upper lower, I'll explain that in a second. But upper lower means that this matrix does not require a lot of information to unfold. Make sense? Okay. So you represent each word using a low dimensional continuous vector. Typically, dimensional is going to be 25 to 1,000, even for the English language, like the 500,000 words. The reduction approach is what we call SVD. It's called singular value decomposition. And this is a very neat technique. And you do that over the co-occurrence matrix X that we had in the previous slide. And so what you do is that you factorize X into U multiplied by E sigma multiplied by V transpose. U and V are going to be the lower and upper matrices that I mentioned earlier. And sigma is going to be your core matrix of choice. It's going to be the low dimensional matrix. And you retain the top K singular values to obtain generalized low rank approximation. I don't want to talk about limitations, but I want to show you like how it works in real life. So this is a code that you can just go to your home. Once I give you the slides, this is code you can copy. And what it does is that it just like imports some common functions from a system and then get you the word representation of that and then as words vector and then calculate the co-occurrence matrix, just like, put it out there and then calculate the decomposition of that matrix. The decomposition is going to be USVH. It's going to be the U sigma that we had earlier, or the sum sign, and then V. Okay, VH is going to be LA. LA is defined here as some. It's going to be linear log ln L from MP from the NumPy, and so it's going to be LA from it called SVD, the decomposition of X, and then you say that this is not a full matrix. Okay. If it is full matrix, you can basically indicate it's full matrix. And so what you will get a bunch of basically values in U, S, and VH. And if you print the first two columns of U, for example, you will be able to see how the individual words that we have here in words would look like in Cartesian. Why do we have two? Because this is XY, right? And so NLP and deep are defined by one another. Flying, learning, and enjoy are this spread. Like and enjoy, even though in reality they are close by one another, they're a little bit far, and so forth. Take that representation, right, of the words, and it's going to be low dimensional. It's no longer like the 7, 8, 10 dimensions, 2 dimensions. That is going to be the first and second value of U. Okay, good. This is great. This is something that you can do in an easier fashion than, say, for example, word to vec. But what are the problems with X itself? Well, X itself is for all possible words out there. You see this X here for I, like, enjoy, deep, learning, NLP, and I forgot flying, right? So for all words. And some words are just not good at defining any semantics. What are those words? Like words like the, he, has, a. Those occur extremely frequently. And so if you include them in this definition, they will bias the definition. They will bias semantics. So they will create syntactic patterns to basically dominate the statistics and dilute the meaning. Okay, so it'll be like spikes for those words, even though they did not really add much for meaning. And they are used for syntax, right? So we use like A is for singular form, that for define, and so forth, right? Okay, carry on.
They dilute the statistics.
Yes.
And distort it.
Yeah.
How are you going to be able to create a good algorithm without using those words? Like how would you?
Here we are talking about like the what do you call it? Let's call it the Stone Age of machine learning, of AI. Before we get to like good juicy stuff. So I'm telling you, well, nobody uses that right now, except like for simple applications. So I'm giving you like the simple things. And then before I get saying like, no, this does not give you like, the coherent language generation, all the problems. We will not be able to get like good syntax. We'll get some good semantics, but not good syntax. So you have to add something on top of this. Alone itself does not really, basically solve a problem or give you a good outcome. You not add variables. You add something called attention. you add like even a more refined, use this one as an initial embedding, and you refine this embedding with something else. You learn to encode some other beautiful things like here you get semantics, good semantics, but then the syntax itself, you learn it separately and so forth. Let's not jump ahead of our like story that we're trying to tell here and just like basically try to absorb what we have here of problem. The problem here is that X itself is very nice representation. It's based on co-occurrence, a real co-occurrence, but has some problems. One of these problems happens with those function words. Those function words, if we include them in this X, in this initial representation before we decompose it, then they are gonna skew our co-occurrence representation from what we're trying to achieve here, semantics, into syntax. They will be syntax heavy, right? So mitigation strategies, you can do a lot of things. You can, for example, say cap the frequency of those words to a given certain value. So this is what we call count clipping. You clip the count. Or you can just like ignore them altogether. We do not really care about them because we do not define the meaning. We define the semantics, the syntax, not the semantics, and we ignore them. Ignoring them means like capping them to 0. Okay. Other refinements, you can have rammed context windows, like assign higher weights to closer context words. Like for example, the words that are so close to one another, like I like define each other very well, compared to or like like this is better. Like what does he say? Dancing and flying. Let's say like dancing is my first option, flying is my second option, right? And so it makes sense to have that something that is close, too close to a word, to have a higher weight than something that is coming later. Okay, so you can do that. What we call RAM window, like a context window, where you assign higher weights, closer context words. You can also do some correlation-based measures, like use the Pearson correlation instead of the row counts themselves, like how correlated is one or another. Open questions oftentimes is that what kind of other normalizations or weighting strategies that could further reduce syntactic bias while preserving semantic structures. You can do a lot of things with that. You can basically heat things up, you can cool them down, you can truncate, you can cap frequency, you can do a lot of things. Yes, you have a question?
So it's a problem, problem with this, words that you're flipping end up, you're flipping them and they mess up
the semantic, the meaning.
It's also messing up the meaning of what you're actually.
Well, okay, so I want to make a distinction. There are word meanings, like the word in itself, abstract, has a meaning, and there is a contextual meaning. I'm talking, like when I say semantic, I'm talking about like the word itself, not the context. And the context, indeed, syntax influence the semantics, right? This is a whole different world. This is like a chapter 17. Yes, not there yet. No worries. It's a very good question. So, okay, so here we had count-based kind of representation, right? So we go over like the entire corpus and then get our co-occurrence. Count, right? How often a word happens with one another. Also, you can do the estimation, like, have direct prediction models where you have not the count, but some probability, estimation, okay? Probability. So what is the trade-off that we have here? So there is a trade-off always between the count-based and the direct prediction-based model. And so the count-based model, it's very fast to train. You do not have to optimize anything. You can imagine that the direct prediction models, like the word-to-vec, right? You have to train on something and get like some values and then do like gradient descent and all of that, and then get some fancy representation. Or direct count is that you have this window, you slide the window, do the calculations, and then you do composition, and then you have your matrices. So for the count, I hope I convinced you, it's very quick to calculate, right? Over one slide. It's very fast to train and calculate. It's efficient use of global co-occurrence statistics. So this is like, how often a given word appears with another word. Primarily captures word similarity and disproportionate influence from very frequent words, because you can control for them. You can truncate them, right? On the other hand, direct prediction models, they scale naturally with corpus size, right? And so they are less efficient. They have less efficient use of statistics. If you care about like exactly how often this word happens with another word. And why you care is that sometimes you want to debug your model. You want to find out like, okay, so if it happens very often, I don't really care about this kind of particular meaning, in my language, then I can reduce this frequency. In the direct prediction models, you do not have access to this information, the statistics. Achieve stronger performance on downstream tasks because they are like fine-tuned in a way, and capture complex linguistic patterns beyond word similarity. So they can capture actually contextual information. Make sense? Okay, that's the thing that you were asking about. Yeah. Any questions? We can do even more. We can encode meanings. You do not have to do things only with the frequency. You can do them with relative order. Like, for example, if I divide how often a given word happens over another word, right? That is a predictive capability. Then I'll be able to get the meaning, relative meaning. And that's what we try to achieve, encoding meanings. Encoding meanings with ratio of co-occurrence is one approach. So the key insight is that meanings can be captured not by the raw co-occurrence, but by the ratio of the conditional probabilities across context. What do you mean by this? So, for example, comparing the probability of X given ice and probability of X given steam reveals latent semantic attributes of X. Make sense? Like, I'll give that an example in a second, but here's the example. Say, for example, the physical state is going to be solid versus gas, and the material relevance is going to be water related versus unrelated, whether something is water related or unrelated. So the interpretation of the ratio, if the ratio is large, it indicates strong association with ice. Make sense? If the ratio is small, it indicates stronger association with steam. And if the ratio is near 1, it means that you have shared or neutral semantics. Okay? Make sense? Are we good? Here is the example of this. So, for example, you have X is of your choice. X is the value that you want to kind of find out the semantic similarity of it. And say, for example, let's see, so you have X solid, X gas, X water, X random, neither. And then let's say, for example, you have a P of X given ice, solid and ice, very high, very large quantity value. And for being gas and ice, X is like gas given it is ice, it's going to be very small value, and so forth. And so steam for the gas, X given steam is going to be very high of a value, and for X and being steam and solid at the same time is going to be very small. Then you can have the basically the ratios of the co-occurrence, right, to define the latent behavior of X. For example, the probability of X being ice divided by probability of X given steam is going to be large, or small for the gas and steam is going to be small. And that is by simply dividing those values that we have here, the large, small, small, large for gas, steam, gas, ice, and solid steam, solid ice. So the relative ratio can highlight some relative semantics about a hidden X. Any questions? How many of you love math? Like math? You just like show your hands up. Be proud of yourself. So math does not bother you, like when I explain some formulas here and there? Okay. But you are in the minority class. So you are like the minority class. So we'll try to put some math, but not as much of math. And I'm not going to expect you to basically have that for exams or whatnot. Oh, really? Okay. Well, I mean, my son got us 3 in high school. So, so much so his teachers said like, hey, stop taking those classes. What are you going to do in college? So it's not difficult. It depends on your training. But math is fun. So let's have some math here. And so the idea here is that how can ratios or co-occurrence probabilities be dismissed, basically represented as linear semantic occurrence using something called log bilinear models. And so we represent the words as vectors eventually. And the inner products, somebody asked about inner products. The inner products is going to be basically encoding the log probabilities. And so, for example, you have Wi and Wj. Those are vectors. Multiplying them, inner product is going to be the equivalent of calculating the log Pi given j. or wi given wj. Okay, make sense? Questions? So this probability that we're talking about here, right? The probability of x given i's is basically something that you can obtain indirectly from the vector representation of wi and wj. And you can use the vector difference to capture the probability ratios. So for example, for 3 words, let's say x, a, and p, you can have 3 vectors, wx, wa, and wp. And the difference here for a and p is going to be wa minus wp. And then you multiply that by wx, and that's going to be equivalent of this probability calculation of the bx given a over px given p in the log. Make sense? So we don't have to do any log calculations or any divisions or anything like that. You have vector representations, and you just either multiply them by one another to get the cosine similarity or the inner product, or you can do difference, pairwise difference multiplied also to get like the ratio of the logs. Okay, make sense? All good? Are we good? Okay. How do we evaluate the quality of the vectors? So you have a vector now, vector representation for words. How do you tell if it's good or not? How can you tell? Like, it's like a bunch of numbers. I was like, you are very happy with it, and just good, looks good. Those numbers are like 2, 3, 1, 5. Where to like draw the line, right? Well, we would not leave it for you to draw the line. So there are 2 schools of thoughts for evaluating those vectors. One of them, you evaluate them for their own sake. And one of them, you ask others to evaluate them for you. And others, by others, I mean other tasks. How good they are doing for specific tasks, downstream tasks, okay? And this is called, the one that looks into basically the actual representation is called intrinsic evaluation. And then the evaluation that depends on others is called extrinsic. So let's start with the intrinsic. So intrinsic evaluation targets specific isolated subtask like similarity or analogy or whatnot, specific to the given word. It's fast and inexpensive to compute. You do not want to build anything on top. You can look at the similarity of words that are actually similar in real life. And if they are similar in the representation, then this is a good representation. If they are not as similar, or maybe like words that are not as similar are more close in the distribution to one another than words that are actually similar, then you are in trouble. Make sense? Are we good? Make sense? Yeah, you. What's your name? Yeah, you seem like spacing out. Right. Yes. What's your name? Zach. So does it make sense, Zach? Yeah. No, not partially. It should be like, fully. So let me explain again until you understand it. So the intrinsic here is that what we care about is that we look at the individual representations, and we want to see if they are good or not. And here what I'm saying is that we look at targeted specific tasks for evaluation. And so here I want to do similarity, let's say, is my task of choice. So I have a bunch of representations, like vectors. I have it for good and like say bad, let's say, good and bad. They happen in the same context, but they're not the same, right? They happen in the same context, but they're not the same. They're not similar meaning-wise, not similar in that sense. But good and goodness. Let's say that good and goodness in this similarity measure, like say cosine similarity, had a larger value than good and bad. A larger value means that they are dissimilar. Good and goodness is supposed to be like very similar to one another, but they are dissimilar in this similarity world. Then this is a bad embedding, bad representation. Otherwise, it's a good representation. It's very simple, right? You look at the word itself and then have some simple metric that you can use for evaluating how good it is when compared to something that is similar in real life. Okay, make sense? So you target specific isolated subtask, fast and expensive to compute because you don't have to implement anything else. You don't want to do sentence analysis or understanding like a larger task like NER or whatnot. NER means name entity recognition. It's useful for probing and understanding the embedding behavior and limited practical value unless correlated with the downstream task. The reason is because a single word does not define so much, right? The word is defined by a larger context. And many of the tasks that we care about, like NER, analysis, whatnot, are holistic in a sense that they combine meanings of multiple words, okay? And so despite having words that might be above or below the bar with similarity, you might be able to achieve better or maybe worse in downstream tasks. On the other hand, the extrinsic evaluation, extrinsic means external, something external, it measures impact on the real world end-to-end task. For example, it could be NER, parsing, sentiment. So you start with your representation and then build this pipeline of starting with the embeddings and then applying this embedding to the NER task or sentiment analysis task, and then find out eventually, is this sentence in which the word appears, is this sentence positive or negative? And if you are accurately able to say that it is, say, for example, positive when it is positive, that means the underlying embedding is good, despite the small, impurities that you have in the representation. Make sense? Good? But you still have to build your sentiment analysis approach to be able to tell that those embeddings are good or not. Are we good? Okay. It's computationally expensive and time consuming because you have to build this task. And performance change may be confounded by other system components because, again, sentiment analysis is not only about the embedding. It could be about like the learning approach that you are doing over those embeddings. So there are multiple components that themselves can influence the output of the system. And one of them is the embedding. Make sense? One of them is the embedding, meaning that it can work well on sentiment analysis, but may not work well on NER. Possible, right? So this is complex evaluation. And a strict comparison, if replacing only the embedding module improves accuracy, it is a clear win, but it's not always the case, right? Because other components might play into the performance of the system. Okay, here's just like too much contents. This is new content, by the way. Too much contents about going with this over again. So intrinsic evaluation, the focus measure the quality of the embeddings on tasks that directly is the word similarity. And the methods that we have, there are multiple methods. You can have a word similarity task, like use a human annotated datasets, like that those words are similar to one another, and then find out if the embeddings themselves are similar. So this is called like word similarity task. Or you can evaluate cosine similarity between the vectors and compared to human judgment. You can do the analogy task. You can do the clustering, grouping words, and then finding out if like clustering over the embeddings, over the vectors. And then you can tell if this is a good representation, if words that are similar to one another, you can look at them by your eyes. If words that are similar to one another are in the same cluster, and words that are dissimilar to one another are in different clusters. Make sense? Okay. So there are multiple methods that you can do for that. And they are like this bite, maybe it's kind of complex to explain them, but they are very easy, relatively speaking, because you focus only on the embeddings. You do not have anything else to evaluate based on. Clustering, yeah, but it's clustering of the embedding. Make sense? Are we good? Okay. Advantage, quick, interpretable, independent of specific NLP applications. Disadvantage may not reflect the performance downstream task. Yes. Yeah. Yeah. Ooh. You want that to be ideally reflected into the actual downstream task. But what I said is that the performance of the actual downstream task is not only dependent on that representation. It can also be influenced by, say, your choice of learning algorithm. Like, is it CNN versus CNN is not used. ANN versus RNN versus LSTM, by LSTM, whatnot. We'll talk about that later, downstream. Still very good. It's still, exactly. It's still very good, but will not give you like the great verdict. Like, oh, this is a great one, and I can, great embedding, and I can use it in many tasks. I don't want to say everywhere, in many tasks. Okay, make sense? Okay. Any questions? All right. So the extrinsic is like, what we just talked about earlier is going to be done with other tasks, downstream tasks like text classification, NER, machine translation, question answering. And depending on the quality of the output of those tasks, you can tell that like the embedding is good. It's not easy, but it's good. Directly measures the practical utility, because eventually the goal is not really to build those embeddings just like to share them with people online, but just use them for actual tasks. And so, you can directly measure that practical utility and reflect the real world task performance. Disadvantage is going to be very expensive and is going to be task specific. Any questions? All good? How is the pace? Okay, so I'll stop here a little bit and tell you a very funny story. And so I read those feedbacks that I get at the end of the semester in the evaluation. And middle of the 1 year, I had some personal issues outside the classroom. My mom passed away, and in middle of the semester, I stopped like clapping and jumping and doing that, and the students were very disappointed. So much so, a few of them 2 semesters ago. Yeah, you were with me. So so I started clapping and whatnot, right? I did not communicate with the students that something happened. But then they thought that it is weird that they had to mention it in the feedback, right? It's not about the quality of the course, but the clapping. All right, so, okay. Any questions? All good? Okay, so it's good when it works, right? It's really great when it works. But we are here to understand the cases where it does not work, right? And so, I mean, for good or bad, words in the language carry multiple meanings, right? So the word bank, we said that multiple times. Bank can have multiple meanings, right? It could be like Bank of the River, the financial institution, the bank family from the Fresh Prince of Bel-Air, and so forth, right? So we have a lot of those. And so we want to add this small ingredient. We are adding ingredients one by one, small ingredient that solves this problem. And the ingredient that we have here is called word sense. Okay, word sense. So what is word sense? So words have multiple meanings. Ambiguity is common, especially for frequently or historical words like pike. It could be fish. I have a single slide about this one, or a whole slide about this one, about the word pike, because I was surprised that pike has so many meanings. So I'll get the meanings even in Australia. So pike has many things. Challenges with word embeddings is that aesthetic word embeddings like word-to-vec assign one vector per word, and those are going to collide those meanings. Like bank is going to be a single vector for bank, not like bank, the family name, bank, the institution, bank, the river. Okay. Do they capture all meanings or create a mess? They create a mess. Solution is to have this contextual embedding. So models like BERT assign different vector based on context, help resolve the ambiguity dynamically. You do not know what is BERT. We'll talk about that later. But something like called BERT, right? A model, fancy model does that. Is it the only way to do it? No. We have multiple ways to solve this problem. I'll give you a few examples before I go for the techniques. So word sense examples, we have like bank, it could be the financial institution, river bank, action of banking, that is tilting, storage, that is data bank, or just verb, bank on something, trust or rely on. Word sense, another example is bike. Bike could be like a pike is a sharp point or staff, type of fish, railroad, etc. Even in Australian English, bike means to pull out from doing something. Like something great, we know something, right? We learn something. In Australia, it means something else. So it's great, okay? So we want to solve this problem. Do you want to solve it? Do you want to solve it? Yeah, super problem. So we do something called a global context solution. So you have a global presence of a word, and you want to differentiate between those different presences. And so the global meaning is in language presentation is basically local characteristics capture syntactic proximity, but many NLP tasks require understanding global semantic structure. And so the modern representation learning addresses this using the following mechanisms: attention-based mechanisms, contextual embeddings, and topic modeling. Attention mechanisms is one approach where you dynamically weight the relevant words or tokens across the entire sequence, enable long-range dependency without fixed context window, and form the core of transformer architectures, and allow models to focus on semantically important context, okay, for that representation. Contextual embedding, where word representations depend on the entire surrounding text, not a fixed vector. Same word can have multiple different embeddings. This solves the problem. and it's used in models like BERT, we mentioned earlier, and GPT, and captures syntax, semantics, and discourse levels information jointly. Topic modeling is the final one, where you represent documents as mixtures of latent topics and capture global thematic structures. Useful for document level understanding, provides interpretable global signals. And the key idea here is that global meanings can be approximated by latent semantic themes. This is the final slide. So this is what we mean by it. So if you look at this slide, this is just like captured image. So if you look at this slide, for example, the word jaguar can have multiple meanings. Jaguar is to do with jaguar hunter, the animal. Jaguar with a string cast, drum, keyboard, whatnot is like a brand of something. And then Jaguar can be the car, the luxury car. And so forth. And Jaguar can be the software, right? So you can have multiple embeddings for it based on the context, right? Make sense? And you can label them like Jaguar 1, Jaguar 2, Jaguar 3, Jaguar 4, Jaguar 5. And it's what we mean by word sense. And that answers your question in the back. That answers your question. So basically, you can create multiple vectors for the same word. Does it matter? No, it doesn't matter, because you just like have them as numbers. That's it. Any questions? No questions? Any questions online? No questions online. That's it. We have attendance here, and I'm going to be sticking around for a couple of minutes if you have any questions. Let me just stop this recording.